Hi, this is Karthik, a master's student in data science from Cardiff Met University. Today we're going to have a look at my project for a module called Programming for Data Analysis. In this module, our project was to build a predictive neural network. The problem which I chose for myself was a multi-class classification problem to predict human activity data. So the basic premise is we are going to collect data by doing regular daily activities like walking, jogging, jumping, and this data is going to be recorded with the help of smartphone. We have a lot of sensors in our smartphones, and an application called MATLAB is useful to record those readings as we go about the activities. So what you see on screen is an excerpt of the collected data. So there are four sensors from which data were collected. These are acceleration, angular, magnetic, and orientation data. The original format with which they will be saved in MATLAB is a .mat format. So these activities were performed at intervals, and then using MATLAB software, we converted all these files into an Excel file. So that was regarding the data collection. Next, if we move on to looking at the data, getting to know the data, what procedures we need to perform on it, etc. So when we look at the raw data, initially we find that the initial few values and the final few values are skewed. This is because those represents the time it takes for us to press the record button and then start the activity. Similarly, we take out the mobile phones from our pocket and then we stop the activity. So the very first data processing we have to do is remove these end samples. So these are for the three activities I chose. You can see that all activities have that skewed nature in the data. So once that is done, we consolidate all the files for each data, walking, jogging, and jumping, because they were performed in iterations and not continuously. And then we check if there are any null values. There are no null values. And then we check what is the count of data for each activity. We see that it is different for the three activities. So each activity had, the least activity was jumping. It had just over 11,000 data points. So we sliced all the activity data so that the data sets are equal. Next, we consolidate all these data sets into a single frame called full DF. And here we can see the various information about the data, the mean, standard deviation, etc. Similarly, this is for the same data, but it is scaled. So one of the things we have to do with numerical data is to scale the data before we feed it into the neural network, because each of these variables will be on different scales. Next, here we can see the histograms of corresponding sensor variables. I put in a way that it can be compared easily, walking, jogging, and jumping along the columns. So this is for the normal data. Again, box plots for the raw data. Here we have the same histograms for the scale data for each activity. We have box plots for the scaled activities, and then we have scatter plots. Now this scatter plot differentiates each activity by color, and we can see that there's a lot of overlap here. So what this says is there is really no, we really can't easily select variables out of these. There is no redundancy. This can be seen from the box plots as well. If we take a look at orientation, for example, there is some overlap in the range, right? So we cannot specifically say which variables are important. The classification will be done on a combination of the values of all the values instead of just one or two variables. So that's just the nature of the data we've collected. If we collect the data again, it might again be different. So these are line charts to see each variable, how it varies along each record. So we can see that there is a difference between the different data sets. After exploration, we save the data in as an external file so that we can use it in different notebooks. The second step is we want to develop an artificial neural network and then optimize it to perform well. So before we do that, we have to do some processing on the data so that it is ready to be fed into the neural networks. First thing we are going to do is import the file which we just saved in the other notebook, and we are going to split this data into three sets: training, validation, and testing data sets. So we've taken 80% of 80% of the total, which is nothing but 64% for the training data set. 16% of the data goes towards the validation data set, and 20% of the data goes for the testing data set. You can see the various columns in the data set. Now we separate the data into inputs and outputs here. So X denotes an input and Y denotes an output. So for each training, validation, and testing data sets, we will have two data sets. One will be the input and one will be the output. Here we can see the output column of the training data set, which is Y train, and it has all the activities. The next portion of processing is to feed it into a Keras neural network. These data sets or data frames have to be in the form of arrays. So we take all the input data sets, xtrain, xval, and xtest, convert them into NumPy arrays. For the output column, however, we will have to one-hot encode it because neural networks do not work with string data. So we use label encoder from sklearn module, and that will give an integer value to each of the activities. So if you see here, we do an inverse transform of 0, 1, 2 in the label encoder, and then 0 is mapped to jog, 1 is mapped to jump, and 2 is mapped to walk. Now we plan to use categorical cross entropy as the loss function, so we cannot feed integers into the network. We'll have to feed binary data. So we use pandas for that. Once we fit the label encoder, we use pandas to convert it into a binary data set. So you can see here that it is converted into 001, 010, and 100, etc. So this, once we fit the binary data, we again convert the output as all the output data sets as arrays as well. So here you can see this is the input array and this is the output array. Here's the shape of those arrays. We have 12 variables in the input with 21,000 odd rows, and the output training data set has the same number of rows but with 3 outputs, which are the binary encoder outputs. Next, we just define a simple model to do a trial run. We do that here. We add an input dense layer, an output dense layer, and one hidden layer with 2000 neurons. 2000 nodes in the hidden layer. Now the output layer should be activated with a softmax function because this is a multi-class classification problem again, and for any classification problem, softmax is a better choice. And the output layer should also contain the number of outputs we are expecting. So for example, here we have put 3 because we expect 3 neurons to map to each of these digits. Based on the probability of output at each neuron, we will pick the maximum probability. So if we have 10% probability, 10% probability, and 80% probability, so we will convert that output to 001. Alright, so here is a summary of the model. We fit the model with our training data set and validation data set. initiated with a batch size of 10 and epoch of 50. Initially, we've defined the optimizer as Adam optimizer. So when we fit the model and predict the testing data set, this is the confusion matrix. This is not really a good confusion matrix. We can see that there are a lot of false values getting mapped here. Only the diagonal shows the true values. So the next step is to tune the model or optimize the model by varying different parameters used in the model. So first one is we tune for epoch and batch size, and we use grid search CV module for that, which uses the Keras classifier wrapper. It takes in Keras classifier wrapper as an estimator, and it parameterizes or the various options which we've given. It uses them as parameters and runs through every combination of the parameter grid we put in. So the best batch size came out as 32, the best epoch, along with a combination of 200 epochs. So next we tune the optimizer by putting in those values, and the best optimizer came out to be an Adam. Next one was we tuned the number of neurons for the single hidden layer which we have, and that came out to be 3000. 3000 nodes. The nodes in the neurons. So ideally, all these combinations would be done with a single parameter grid, but it requires a lot of computing resources which we do not have at the moment. So we are just following this process to optimize it step by step as best as we can. Next, we use k-fold cross-validation to check how the optimized model performs, and we get a good score here. So next is, again, with this tuned or optimized model, we are fitting in training data and validation data, and we look at the learning curves, which is the loss in training and validation, and the accuracy in training and validation. So what we see here is, we've given a limit of 200 epochs, but both training loss and validation loss keep decreasing even at 200 epochs, right? Which means that we have to increase our epochs. And we also see that the validation curve is not smooth, it is very noisy. And this could be one of many reasons, but majorly whenever we use batch size, a smaller batch size gives rise to this problem. This is empirically known, and a lot of resources over the internet, just a simple Google search will mention this problem. So what we can do is, I've written down a few reasons here, and like I said, we can try changing the batch size. We can improve the batch size, because having a small batch size makes the model fit to smaller batches and gives more affinity towards those values, or a small number of values within those batches. But giving a large batch size will help train the model towards a larger or a greater range of values, and then that will smooth out the validation curve. Now we can also try using dropout layers, changing the learning rates, etc., to see what happens. So I did a few trials by changing the parameters. So this was trial 1. Obviously this did not go well. There is more noise introduced into the network now. Trial 2 looks better, but the validation curve still, the noise is reduced, but it's still noisy. So this might look worse than the first one, but that's not true. The reason is This is on a scale of 200. So since all this noise is spread out, it looks more neat, but this is on a scale of 500. So if I drag this graph or stretch this graph, it will be more neat. So coming to trial 3, again, not good, because you can see that even at 500 epochs, the loss is pretty high. Trial 4, the curves overlap altogether, right? It's like the training data set and the testing data or the validation data set are equal. The model has seen the validation data set already in the training data set. So out of these, trial 2 or the output of the model used here in trial 2 seems best. Now, if we had computing resources, obviously we would give all the parameters in one go and get the best outcome, but unfortunately we don't. So the main purpose of doing this is to get ourselves familiarized with the process of tuning a predictive model. Next we have now we use that training to finalize model, and then we fit it with the training validation data set and then predict it. This is the confusion matrix after we tune the model, and you can see that it is improved a lot. And these are the performance metrics. Accuracy score is high, log loss score is low as it should be, and ROC 1 versus rest is 0.9, and it's high as it should be. So this is our model. Now we are, as an additional step, I implemented another model from a research paper. It is a convoluted neural network, a deep convoluted neural network, and in this paper they convert the data into using a window function. They convert it into time steps, or for example, you can see that it is a 3-dimensional array with 128 time steps, each having 6 variables each. 6 variables because this paper mentioned that these 6 variables are enough for classification. So we just dropped all the other variables, and you can see that the dimensionality of the data has changed. We no longer have tens of thousands of data, but because we put them into groups of 128, the number of sample data has reduced. Now the CNN model, the preliminary model, was created to mimic the architecture mentioned in the research paper. We fit the data and analyzed it, but looking at the curve, it was really bad. You can see that training loss is 0 all along. So to overcome this, again, the tuning for this was done randomly. It was not put into the grid search CV, because this is a deep neural network, has many layers, and again, computing resources are constrained for me. So I just randomly tried, and this was the best model I was able to get. So with this, again, we fit the data on training and validation, and then predicted the testing data set. But this model performs better as well. And then when comparing the metrics, it is close to the model, to our model on the RSC curve part, but you can see that the log loss is a lot higher, which is a negative point for this model, and the accuracy score is less than our model. So the conclusion here is that a simpler neural network prediction model works best for this case when compared to a deep neural network, a complex neural network. All right, thank you guys.